Hi there, welcome to the lab. Today we're going to have a look at this Aneng. This is a model 626, and this is a totally different kind of form factor for a multimeter, so I thought we'd give this a try. And I'd just like to say that if you found this video to be helpful, please give it a thumbs up and subscribe to the channel. Your questions and comments are always welcome, the feedback is appreciated, and it does help me figure out where to focus my activity. And now, let's get into the box. Looking in the box here, we've got a set of probes. They're what I'd consider, they're kind of sharp. These are what I consider full-size probes. And the connectors are straight through connectors as opposed to right angle connectors, probably because of the form factor. And this is sort of standard PVC, and it's got the usual sort of sheaths to raise the cat rating on the probes. There's a typical K-type thermocouple there, a USB-A to USB-C charging cord, the multimeter, which is in plastic, and I have to say that is the most interesting multimeter form factor I think I've ever seen. Charge that up in a minute. And a very colorful instruction manual. And it looks like it's got English and Chinese here. And specifications in a variety of languages on the back. But the bulk of the manual is either English or Chinese. All right. So the first thing I'm going to do is charge this guy up. I've plugged in the cord, and while it's charging, there's a red light that comes on here at the bottom. We can see now that when the battery's fully charged, the indicator at the bottom turns green. Let's power the unit on and have a look at the basics. That lights up. It's a very bright display. A lot of information to see here. And so we can see all the different modes here around the perimeter of the display. And this little indication means that it's an auto power off mode. We can see right now that it's an auto mode, and there's a temperature sensor there showing the current temperature. I think that's there a lot of the time. There is a flashlight here. Quick press there, turns on the flashlight on and off. There's a data hold button. We'll try that in a second. We get into another mode. Then the inputs are along here on the side. The non-contact voltage sensor is up here somewhere. It's labeled there, if you can see that, NCV. And we saw the USB. There's a little stand here. So it'll stand up on the table like so. But otherwise, it's an interesting form factor. Now, there are all these different modes here, and so we get to the modes by pressing the cell button, so we have to kind of go through them all. There's auto, DC voltage, AC voltage, resistance, continuity, DC current, AC current, frequency, non-contact voltage, live wire, temperature. We skip over the H. That would probably be for inductance, but there's no inductance in this unit. Then there's capacitance, diode check, AC millivolts, DC millivolts, and then back around to auto. Now, one thing I found out is that a little bit of a shortcut here, pressing the power button always takes it back to auto. So we can kind of spin around a little bit, and that'll come back to auto. And another nice feature, you might have noticed this as I was going around here, when I get to the current ones, you can see that it's telling me about where to plug the leads in. And so if I plug the lead in to the voltage input, which is this top one, then it doesn't make any noise like some do, but it does have this lead warning. And I have to plug the lead in to the current input down here, and that goes away. And that's a feature that I've only seen before in some very expensive meters like the Brymans actually keep that warning on, and when I unplug the probe, that warning comes back. So that's a very nice feature. This is probably only the second or third meter that I've ever tested that has a display like that that senses the presence of the probe. So that's very, very nice. And now let's give the and now let's give the features a try. Now let's test out the features. I'm going to start here with auto mode. You know that I'm not a big fan of auto mode, but it's a feature on these meters, and so I feel a little obligated to give it a try. And so I'm going to start it out with the calibrator set here to 0 volts, and we'll see what happens. And so it immediately thinks that that 0 volt signal is not 0 volts. It thinks it's continuity. And so the buzzer is going off, as you can hear that. Now let's start increasing the voltage a little bit here. So now that's 1/10 of a volt. No longer is it seeing that as a continuity signal, but it is still seeing it as a form of resistance. We can see the ohm symbol there. Now it's actually detected at 0.2 volts. It's showing that as millivolts. And so that's actually very good. I like that. We'll go down again. Now that it was in the voltage range, coming down to 1/10 of a volt, we can see here that's showing still in the millivolt range. If I go to 0, it's going to go back to a resistance mode. So that's very, very nice that it only takes 0.2 of a volt for it to read into the millivolt range. Now the other thing to try out here is resistance, and so that's 20 ohms of resistance. It is seeing that as a resistance, and so because it's below probably about 50 volts, the continuity buzzer is going off. And at 50, the continuity buzzer turns off, and we see the resistance reading there. So although I'm not a huge fan of auto modes, I will say that this seems to be one of the better performing auto modes because it only takes 0.2 of a millivolt or 0.2 of a volt in order for it to get out of that confusing zone where it's not sensing values properly. I now want to test DC voltage. One of the things I noticed as I was about to change modes is I wanted to get into the dedicated voltage mode, and it won't let me change the modes because the probes are connected right now. So if I disconnect the probe there, it falls back into auto. Now I can change mode and I can be into the dedicated voltage mode. And so now let's go down to 0 volts, connect that, 0 volts, showing very well here. 1/10 of a volt, that's pretty close. 0.2 of a volt, once again, really close. We'll go up to a full volt, off by 0.002 of a volt. We'll go up to 5 volts. Also very, very, very good reading there. 6 volts. Now this is a 6,000 count unit, so we'll see what happens when we go to 6.1 volts. That's really good. 6.2 volts, and there you can see we've lost that leading digit now, and it's gone down and it's showing 6.1 19 for the 6.2, still a very good reading. And now we'll go up to 10 volts, 999, another really, really nice reading there. And then the calibrator maxes out at 11 volts, so that's just fine. So that's actually very nice performance across the DC voltage range. Looking at millivolts, the calibrator is now set to output millivolts, and I've got the meter in the millivolt range. You can see it's just showing 0.02 millivolts, so below a full millivolt. Now we can bring that up. That's 1 millivolt. We're showing 0.97, 2 millivolts, 1.97, 4 millivolts, 3.96, 5 millivolts. And it's interesting we don't have a leading digit there. 4.96, 6 is 5.97, and it's 7. So we're generally off by a few hundredths of a millivolt. 8, once again, similar amount of error. So as far as millivolts are concerned, actually reasonably accurate with a fairly consistent amount of error as I've gone through the range here. Now AC voltage, I've got the unity here set up as a reference and the Aneng, and they're all connected. The power's not on. We can see a little bit of ghost voltage on the units. They're tracking fairly close. Let's turn on the power. And we can see that they're both reading about 121.8. And as an added bonus, because we've got that secondary display, the Aneng is also showing me the frequency on the power line. So very good performance on AC voltage. One interesting thing that I noticed is that if I've got the meter in some mode here that's expecting input on this side, on the regular input, when I plug the contact in here, it automatically switches into the current measurement mode. Now in this case it's switched into DC. I can switch it to AC, and pressing the cell button again, it goes back into the DC current mode. And so once I've got a probe plugged in here, I'm locked into that current measurement mode, and I can't put it into the wrong mode at this point. So that's a nice feature. Now looking at DC amps, the calibrator is going to output 4 milliamps as soon as I connect it. I've got the meter in the amp mode, and it did remind me to put the lead into the proper socket, so I've done that, and I connect it. 4 milliamps, takes a little bit. 4.1, 3.9, 4.0. So you can see it's kind of settled in nicely. We'll go to 5. Almost there, off by a tenth again. We'll go up to 10 milliamps here. And it's a little slow to respond, but very accurate. Very good performance here in the DC current. Now AC current, we're all wired up here for AC current. I've got the unity in amp current mode. The Aneng is in amp current mode. And I've got this fan here, which acts as my current load. Let's turn it on and see what happens. You can see more power as the fan starts to come up to speed. And once the fan stabilizes, we can see here 168 milliamps, 0.167168 milliamps or amps. So they're both pretty much reading almost the exact same value, and you can see a little bit of jitter as the current just varies a little bit. So good performance in the amp current range as well. Now looking at resistance, the calibrator is set up for resistance. I've got this in the resistance range. I'll just connect this now. 20 ohms on the calibrator, 20.2, that looks like a pretty good reading. On the meter, we'll go up to 50 ohms, 50.2, another good reading. 100 ohms, off by 0.4 of an ohm. 500 ohms. Now we're off by 1.7 ohms, roughly speaking. 1K. At 1K, we're off by 1 ohm there, and then we'll go to 2K. 2K, we're off by 4 ohms. So that's pretty good. That 4 ohms is a relatively small amount of error. Now I'm going to have a look at frequency. I'm in the frequency mode. The leads aren't connected yet, and so it's sensing some sort of a noise and it's jumping around a little bit. The calibrator is set to 100 hertz. When I connect it, we see that we're pretty much on to 100 hertz, so that's a really nice reading. And the calibrator puts out a 50% duty cycle, and we can see there the duty cycle is shown in the display, so I don't have to press any buttons to get there. Let's see what happens as we start raising the frequency. So we'll go to 200 hertz. That's a good reading for frequency. 300 hertz. Now we can see the duty cycle is rising, and I will say that I have looked at the calibrator, and I found that the duty cycle on the calibrator does shift as the frequency increases. And so I think that's a decent reading. I have some other information. I'll try to bring that up in the overlay. Here's 1000 kilohertz. Very nice. 2 kilohertz. Very good. 3. And you can see that the frequency is very, very good accuracy on the frequency, and the duty cycle 62%. And I expect that the duty cycle on the calibrator is probably rising. 5 kilohertz. Once again, we're off here by what amounts to 3 hertz. So very good performance for frequency measurement from this Aneng unit. Now for temperature mode, I've set the calibrator up to output a signal corresponding to a K-type thermocouple, which is what this would use. We're not connected yet, and so at the moment it's showing what it believes to be the ambient temperature. That's a little bit higher than the ambient temperature in the room. The ambient temperature is closer to 22 Celsius, so that's off a little bit, but now let's connect the leads. Now we can see it's right on at 0. We'll bring that up to 100, off by a degree, 200 off by a degree, and I generally consider that anything within 2 degrees is really excellent performance. 300 off by a degree, 400 still just off by a degree, 500 once again off by a degree. So really excellent performance in the temperature mode. Now let's have a look at diode check. I've got the test box here. So that's a good reading. And that's a good reading. No beep. Lights up the diode there. So it lights up all the diodes in good readings, but just no tone. So reasonable performance for diode check mode. Now I'm going to look at continuity with the supplied probes. So pretty good, but it does seem to miss some of the taps. Let's switch over to a pair of gold-plated probes. Now switching over to the gold-plated probes, you can see that it's a lot better, but it still does miss every once in a while. And usually I find when I switch the gold-plated probes, most meters don't miss anything. And so it is a little bit surprising, given the other performance on this meter, that this is missing some of the taps. We're set up for capacitance. We'll go through the reference board here. This is 100 picofarads. It looks good. This is 1 nanofarad. It's good. 10 nanofarads. 100 nanofarads. This is 1,000 nanofarads. And 10 microfarads. Now let's have a look at the non-contact voltage. I've got a plug here. The hot line is along this edge, and I'm just going to bring that close to the meter. And you can see there about a centimeter out, it starts to respond. When it's right on top, it's quite strong. Moving to the side, this side. Very nice sensitivity on the non-contact voltage. Now live wire detection. I've got the same plug, and let's try the ground spot. That's good. Neutral. That's good. The hot wire. Good response there. And so this meter actually operates the way it's supposed to for live wire detection. Nice to see. Quick look inside. We've got 4 screws here that come up, and then the unit splits open. And the first thing we notice, we can see the battery here, the LED lights here, and then the USB-C charge port there. And one of the things about this unit, which is different from many units of this kind, the connections are actually socketed onto the other side rather than being soldered directly to the main board. And so I'm going to take advantage of that, and I'm going to disconnect these items so that we can have an easier time looking around. So I've disconnected all of the wires now, and let's have a look inside. We'll kind of hold it this way. We see here, this is some flash memory, and that'll be used to store the configuration and calibration information. Looking around here a little more, we've got a PTC here, so there's some input protection there. There's a relay. This relay is used to switch the contacts around because we don't have a physical switch. It's all sort of soft switching, and so that is accomplished with the things that do need to be moved over physically are done through the relay. The contacts on the board, you've got the buzzer here. There's a fuse here. Now the fuse is, and you know, it says 250 volts on the board. The fuse itself is also labeled for 250 volts. And that doesn't jive with the 600 volt Cat3 labeling on the front. So that's a little unfortunate. What else is there to see here, really? I mean, the plugs for the various items, and then the main event here. And so we'll see if that's visible. So this is a CR216 microcontroller. So this is a custom microcontroller. And this CR216 is produced by a company called Crown Rich Technology. The datasheet for the CR216 is very hard to find online, with most of the information in Chinese electronics forums. But I was able to find a copy via the EEV blog forum. It's all in Chinese, but fortunately translation these days is not too difficult. From the overview, we can see that this is a 6,000 count chip that supports a lot of multimeter features, many of which are present in this multimeter. A few of the features of note that are present in the chip, but not in the meter itself, are min-max support, square wave output, transistor gain measurement, and inductance measurement. The presence of inductance measurement in the chip is especially interesting given the H position on the mode selector dial and some other symbology associated with inductance measurement in the LCD display. It makes me wonder if there's a way to somehow unlock this capability within the meter. One thing that's a little bit hard to find on this unit, And I think it's represented by this particular resistor is the current shunt. So I think this is the current shunt on this resistor. If anyone has any other thoughts about that, please put a note down in the comments. This is a very interesting multimeter. It eschews the traditional form factor for something new and novel. This is a 6,000 count meter with a great deal of functionality. The VA LCD display is always crisp and bright. The meter has a rechargeable battery because no doubt the display uses a lot of power and would otherwise burn through batteries fairly quickly. Accuracy in the basic modes like voltage, current, and resistance is excellent, performing much better than the specifications would suggest. With one exception, capacitance measurements were generally better than the incredibly generous specification would suggest. The socket warning and automatic switching for current measurements is fantastic at this price point. The non-contact voltage detection performed very well. On the other hand, the mode selection can be tedious because of the need to cycle through all of them all the time. Continuity did not perform well, even with gold-plated probes that usually make up for the poor included probes. Duty cycle was one of the few areas where accuracy was very far off. It's unfortunate that diode mode does not have that beep. It's one of the main differentiators between the low and high ends of the market. Lastly, the fuse rating at 250 volts doesn't align with the 600 volt claim on the front of the unit. This could be a really nice unit for hobbyists working in a low energy environment. The current mode socket detection is sure to save a few people that might attempt a voltage measurement with the probes in the current socket. However, the tedious mode selection is likely to be a source of frustration. If you found this video to be helpful, please give it a thumbs up and subscribe to the channel. Thanks for watching, and until next time.